Good. Sorry. Let's get started. The goal of today will be finishing the estimation slide, which we're done. And I'm asking our TA to release the latest assignment in the next week, early next week. We have that. Of course, you're given 2 weeks to finish as usual. At least 10 days. I don't know whether 2 weeks, but at least 10 days to finish the assignment. Hopefully 2 weeks. So after we finished, we only left last part, which is a sample size estimation. And after that, we will go to the next thing is what we call the hypothesis testing. And once we've done these two topics, basically you would know the basic tools that underlying all the statistics, right? Basically, we will do estimation. Once you do that hypothesis testing, we're checking whether what you have found is going to be valid. Okay, and this is the standard procedure for any model you're going to do. And when we do ANOVA or regression, the last part of our class or course, we'll be doing these two procedures. So let me finish this estimation topic first. So first of all, let's review what we're doing. Estimation involves a way to uncover or discover what are the population parameter. Why parameter is the number, right? The number we don't know yet. It's just like the mean, the variance, the standard deviation, kurtosis, skewness, and their number, right? The population version. And what we want is to use the sample version to guess them, right? The sample version are a function of the sample. This is called the statistics, right? And to ask the estimator, it become estimator. And do remember that these are all random numbers, random variables. So it means estimator random variables. And when they're random variable, then their mean, their variance, their distribution. So we want to know what are these and do they have good property, right? Because we want to guess things, right? And just to remind you, what are the estimate just particular number, but they are not random variable, and such we don't have any property to say about estimate. And there are two types of estimator. One is point estimate, the other is interval. And point estimate gives you a number, and interval gives you a bunch of number, right? It's interval, right? It's a bunch of numbers. And for point estimator, we have 3 different ways to say they're good. Actually, there are more. But in our introductory class, we focus on 3 of them. And first, unbiasedness. And unbiasedness means that if you have one sample, you guess in this way, the other sample, you guess the same way. And you manipulate those samples, you get the same way, and average of those outcomes is actually what you want to guess. So it's in principle, if you don't repeat what you're doing, in the long run, you discover the truth. And do note that you only do once, right? Or at most twice. But it's in principle that what you get is what we want at the end of the day on average. So that's the idea, right? Just remember the analog I'm going to draw again is like me and football star, right? All of us are unbiased, right? Because on average, we hit the target. But if we want more, right, we want how good are they, we don't look at the efficiency, the variance. If we are closer to the target, then it's better, right? So that means that A is better than B, A is more efficient. And efficiency is only comparable when you talk about unbiased estimator, okay? If one is closer, but on average not right, then it's not comparable, okay? So here I only compare when they're unbiased only, okay? And last one is consistency. Looks fairly complicated, okay? But in general, what it means is if you look at unbiased estimator and if the variance is finite, and it just simply means eventually this variance go to 0, So it's just like unbiased estimator, and the variance actually go to 0. Okay. So that is what it means in general, except some technical difference, but I basically just like go to 0. And a sample mean is a good estimator because it's satisfied unbiasedness, is efficient among any linear combination, and also consistent. And last time we explained in detail why sample variance is a good one. And we need to n-1 because of we have X bar, right? If we know the mu, we know the population mean, we don't need that, okay? So that is very important concept that have to remind you, okay? And after that, we talk about how estimate the standard error of mean, right? Remember, standard error of mean is standard deviation of the sample mean, right? So we'll be by that. We'll talk about the sample proportion. It's also unbiased estimator of population proportion, and sample variance. Here we have a shortcut. It's just replace pi by p, but this is kind of biased. But we will still use this one because we have good estimate of the p of the pi. Sorry. So that's we estimate pi by p, but this is bias. But it's still not a big issue because when we said n is large, when we talk about binary data. So this part n over n-1, the adjustment doesn't really matter that much. And because also p times 1 minus p will be small, right? So it doesn't really matter anyway. So that's why we do that. But if you are serious, we won't do that. Okay. So these are all the formula we have for the binary data. So when we have point estimate, we go to interval estimator, which I will slow down a little bit because I think this is one of the difficult part in this class as well. Okay. So we focus on sample mean because that is the easiest thing to look at. And with the sample mean is going to follow a normal if you from the central limit theorem, or if you assume normality assumption, if the underlying is a bell, you draw a sample mean, it's also a bell, right? So that is a bell assumption goes on in this background, okay? So just to remind you the sample mean, right? It's just either you assume the underlying is bell or this is the bell curve, okay? So the bell curve has mean mu, sigma square over root n. So this is something we have here. So one of the main thing here is, since we know this guy, how good the accuracy they are, right? So we want to know, okay, using this precision, measure the variance to give us a better guess on mu, right? Because you know the probability that X bar equal to mu is 0, right? Continuous variable, particular number will be 0, right? The sample mean exactly equal to population mean is equal to 0, right? So how can we say a little bit more, right? So we just want to say we want to X bar go left by m, which to be decided, go right by m, okay? We want this interval with width to m, okay? We'll have high probability that include mu. Okay, let me repeat the statement again because this is crucial to understand interval estimator is X bar will have 0 probability equal to mu. That is the definition of continuous random variable, right? Continuous, particular the same, it'll be 0. So, but since we know they follow the bell curve, right? So we can say more, right? I mean, although X bar is unbiased estimator, consistent estimator, right? Which means that if you have very large sample, X bar will be exactly mu. That's no problem. But what happens if not large enough sample, right? So we want to have say more. So we want X bar extend left and right by the same amount because it's bell curve, so it's okay to extend symmetrically. Okay, symmetrically both sides. We want this interval with the width to m. Okay, I can catch mu with large probability. Okay, and do note that mu is unknown. There's no probability you can say. The probability can only say is this interval. The interval with large probability catch mu. Okay, mu is somewhere doing high and sit is hiding somewhere. I don't know where it is, but you want your net to catch it. Your net is not fixed, it's random. Okay, you want to grab this guy. Okay, so the math we're saying is we want to have X bar go left and right by m to include it. To make sure that you get it, I just draw it again in case you forget about the details here. So remember, this is X bar is here, center is mu, okay, and the variance is sigma square over root n, sigma square n, right? And what we want is the following, right? It's like, suppose I draw a sample mean can be anywhere, right? But it will be following this distribution, so more likely the center than the outside. And suppose you end up here, right? This is your X bar particular, right? And you would go left by m and go right by m, okay? And I want this interval would include the mu as much as possible, right? Of course, for any mu, for m, right, you may end up unluckily very far away, right? If you go by m, left and right, there's no way to catch it, right? So there's no way any finite m, any m you say, will always miss it, right? Because X bar extend from negative infinity to positive infinity, right? The definition of the normal. So how can you solve this problem? Would be to say you want a majority of them you are going to do will get it, right? So it means no matter the sample mean I got, okay, you'll get many of them, but majority of them would get it, right? So if I want majority of X, I draw left and right by M would got it. It effectively means the following, right? It's same as I'm asking myself, I have mu, I go left and right by m, right? Right? I have large, this area is large enough, right? Then it's dead, right? Because when I draw sample is within this range, when I draw m, it will be included, right? Because if I data is here, right? I go left by m and right by m, it will be included, right? So as long as it's within this region, right? When I draw left and right by m, we're there, right? If I'm outside, right? I draw m will not include, right? So I just need mu go left by m and go right by m is contain most of stuff, right? So what I want is this area is large enough, and I use 1 minus alpha to represent big enough, and alpha is often a small number like 0.1, 0.05, or 0.01, right? Which represent 99% of the time it there, or 95 or 90, right? And if we know the variance is sigma squared over n, so what is the m here? M will be z alpha over 2 sigma over root n, right? Because sigma over root n is the standard deviation, SD. And how many SD you want is called z alpha over 2, right? Why? Because if this 1 minus alpha, right, and the 2n are alpha over 2, right, because symmetric. And this must be c alpha over 2, right? So this definition of that, okay? And if you want, what is the Excel formula will be just norm dot s dot inverse, right? 1 minus alpha over 2, right? So this is the one, right? So that would be, this is the formula for the interval estimator of the sample mean, right? They will be just x bar plus minus this guy, right? Because this is the m, right? So this is the formula behind here. Okay, so this is the formula. And I'm sure that even if you don't know what I'm saying, you just remember the formula and plug in will be fine. Okay, but I try to explain to you to see if I can convince you this formula is right. And after that, you can look at this example again. I just try to make sure that you would follow this. This is just will be x bar plus minus z alpha over 2 sigma over root n here. Okay, and x bar is just 3, sigma is just 4 here, and it's just 64, and 95% means alpha is 5%. So this is just remember it's norm dot s dot inverse 1 minus 5%, 0.05. So 0.975 is the answer, right? So that is the formula that we have already. Okay, so you plug in all the number, you can get it. So you would tell people that your best guess is 3. 95 confidence, you will be between 2 and 4. Okay, so that would be something you would say. And if we don't know sigma square, which is often the case, we don't have information, and we'll use S instead. But if you do that, we need to invoke the important thing is normal assumption applied to the population, okay, which may or may not true. If not true, then this is not valid, okay, but you have to use other method. But assume it's valid, which is usually the case, then this follow the T. So you can see the same logic we apply, but you just change the formula to this one, it's just change to T, right? So if you don't unknown, then use the T, right? Is S here. Okay. So there is some complication of this one. Okay. But when you apply in the practice, it's not difficult, right? Because unknown, variance, and under normality, right? The formula is like this. If you just from that slide, right? You just the formula is like this one, right? And x bar 3 here, right? And S just 12. Root n is just 20, right? The only part is this part. And n is 20, then it's at 19, right? And 95% means alpha is 0.05. Alpha over 2 is 0.025, right? So the Excel is just t dot inverse That's 1 minus alpha, right? So it's 0.975 and 19. Okay, so you will get 2.093. Okay, so just plug in all the number. Then you will say your best guess is 3. The worst case is negative 2.6. The best case is 8.6. Okay, and you can see this is a huge range because your sample size is small, 20. Okay, if you have sample size is much more reasonable, you don't have this problem. Is that okay? Okay. Now the question probably you would ask is, as I said, you want to have a larger sample size, right, to get a more precise estimate. So you want to do in advance what sample size you want to get, right? So that's why it means that we actually do an opposite case. We will give you the precision, the margin error. We want to calculate sample size. We reverse the formula. So here is what we will do in next slide is this is our margin error, right? So we want to give you the margin error. You calculate n for me. So just reverse the process. But let's go for it. Go for it. Okay. But before we do that, we talk about it very quickly about the binary data. For binary data, that is same, right? Because you just remember the formula for the mean, right? It's just x bar plus minus c L2 s over root n, right? And for binary, square root of p over p is the s, right? S is equal to p1 minus p square root, right? So that's why you have this formula. So there's nothing new in this one, okay? And let me show the example here first, okay? Is remember the formula we just said is p plus minus z alpha over 2 square root p 1 minus p over n, right? So this is how you are guessing. Okay. So you have a data, n is 64, sample proportion is 1/4. So what kind of question you are looking at is, suppose you want to ask how many people like your product, right? And then you look at people say yes or no, right? Or do they think the product is too expensive, or do they like it, right? Maybe or this kind of question. Or do they know your product, right? Look at your brand name test, okay? So yeah, 1/4 of people like you then, but probably you want to get it more precise. So you want 95 confidence, okay? Alpha is 0.05, right? 5%. So what you do is P is already 1/4, so you just put quarter here, right? So this is 0.025, this is 0.25, and N is 64, so this is the guy, right? And we know so many times already, 95% normal is 1.96, right? But of course, if you still don't like it, you can just do norm as inverse 0.975, right? So apply all the number, okay, to the calculation. It will show you that the best case is 1/4 of people like your product, okay? And the margin error is 1%. So you will be 15% people like your product up to 35, right? So that will be the best guess for you, right? Of course, if you want to get a better estimate, then you increase the sample size, then your estimate will be getting more accurate, okay? As we said, after that, we talk about 3 slides, 3 to 4 slides. The remaining slides talk about how to get the N, right? Because that is how you do the survey, right? You want to know what should be the N, right? In order to achieve a certain precision, right? Because you want to know this very precisely. You don't want to say, okay, it can be from 0 to 1 always true, right? It's useless. We want to say have more precisely how exact, okay? Depend on how much you want, how large the range, I can tell you the sample size, and then you can calculate cost of doing so. Okay? So here comes to the very last thing. I think the sample size is very important because it gives us the very first question, how much or how many observations we need, how large the sample size we need to have. Because that is the problem at the beginning, right? Because before we collect data, we need to estimate what's the cost of doing so. Okay. So let's look at the question of general case, and we will talk about the binary problem. So just we focus on simple case. We focus on the case where the sigma square is known. Okay. If not known, then rely on the t. That's also doable, but we cannot do it by hand easily. We can use computer. So we focus on the simple case. We can still do things by calculator. Okay. So assume this is known. Okay. The margin error is this one, if you still remember, right? And of course, we ask in practical case, we never know sigma. How can we know that? Okay. In this kind of problem, later you will see there's no problem of overestimating sigma. In that case, we just do bigger sample than we need. We're just more conservative. Okay. So that's why when you don't know sigma square, the easiest case is use the range divided by 6. Then will be the way to estimate the sigma, because data should be most likely within 3 SD, right, or 4 SD. So you can use the range of the data, which you know what by the maximum or the minimum, which is something you can guess relatively easily, right? And in that case, then you can guess the sigma. It gives you upper bound. Okay. So assume it's known. So what you're going to do is to get this is you tell me what precision you want. ME maybe within $100, and within 100 or within 200, within 10, within 2, it's no margin error. You give me this number, okay? You give me the precision, right? If you want 95%, it's 1.96, right? You tell me what the alpha you want. This is what I tell you how to guess already. You can solve for n, right? It's just like high school algebra, right? You have equation, you have all the number except 1, you can solve it out, right? You make n the subject and you square it, right? And then you're done, right? Take n to that side, you can solve this out. And you can see I have a ceiling function here. The reason I'm ceiling because n has to be integer, right? So I run up because run down will not get the thing. I just add to the smallest integer that's larger than that number, right? That is called the ceiling function. Let's see the example. So I have assume I know the population follow a normal distribution with standard deviation of 10. As I told you, how to estimate 10, right? Maybe the data, say, is from 80 to 120. What's that? Like IQ, right? Maybe you're looking at the regular population, right? It should be from 70 to 130, right? That is 6 DVA. The range can be considered as divided by 6 will be a good guess for standard deviation here. Okay. So now suppose you know 10, or you just use the way I described to estimate. Then we want to determine a sample size that have 95% confidence that within 4. Okay. So that is, remember, is ME is equal to Z over 2 sigma over root N. Or you can replace it with N is equal to open bracket. You just replace here ME square and then Z alpha over 2 square sigma square. Okay. And just figure out each thing. 95%, this guy is 1.96. Okay. And M is 4. So this is 4. This is 1.96. And this guy is 10. Okay. Just plug in all the number there. It's 24.01. You take the largest number, the smallest number that is larger than, smallest integer that's larger than the number we create is 25. So as long as you're 25 observation, then you're done, right? So that would tell us how many data you want to get. Okay. So that's very important later when you talk about business applications called A/B testing, right? Then look at how many number you want. Okay. We will talk about some A/B testing in the second half of today's class, because we talk about hypo testing, and hypo testing is the one thing is actually the business applications of A/B test. Okay. And you compare two things, right? So now we know we need 25 observation, okay, to achieve the precision of standard. The margin error is within 4. Okay. So if everything is right, then you get what you want. Okay. So now after that, we tell you the other one. So we just do the binary data. The proportion is following this ME formula. If you still remember, okay, if you know pi, okay, and that means that if you do the n the other side, you get this formula, right? Just n square root n go to that side, m you go to below, and you square everything up, you get this formula, right? So that's nothing deep about this, but just replacing. Well, of course, if you don't like to remember this formula, you can just plug in this number, plug in the number, plug in all this number, and then solve for n, right? That's something trivial. But I know from your high school, you know how to solve this. Okay, so come here to here. Now, the question with the following, right? So if I know 0.4 is the population proportion, say 40% of people like spicy food, right? And you want to do another estimate, right? So you want to see how many sample size you want to get. Okay. You want to do a 95% confidence interval. You want at the end the margin error is 1%, right? So remember the ME for this case is C alpha over 2 pi 1 minus pi square root over n, right? So that would be the ME, right? And we write everything is n is equal to ME square pi 1 minus pi square root, right? So that would be the formula there. So we just know pi is given 0.4. So this is 0.4 here. And 95% is 1.96. That's easy. We know where already. Margin error is 0.1. So just plug in all the number. Calculate. Turn out it's 92. Okay. 0.198. So just 93. Is that okay? Just to remind you how to get 1.96. It's just norm as inverse 0.975, right? Because 95 is the middle, Why? Just to remind you again, why I do that. You want 95 in the middle, right? So it means that the both ends must be 5%, right? So 5% share on both sides, so it's 0.025 on both sides. Okay? And at this point, this is 0.975, right? So that's how we get that one. Okay. Is that okay? So that is nothing very new here, but we tell you very nicely the formula. We tell you that if you know it's 0.4, the observation you need is 93. Okay. But this formula is not frequently used because how can you know the population proportion? If I know it's 0.4, then why I'm doing that, right? So that's why we will be usually more conservative. We'll use the following math technique. Okay, is hopefully you still remember this from your high school. If this is X, this is Y, try to plot what is this graph looks like. This X is 0, Y is 0. When X is 1, Y is 1. And you know this is quadratic. Looks like this. Sorry. This is a, so this is a set face. The highest point is 1/2, 1/4. Still remember that. This is just high school math. Okay. So that means that the marginal error, remember, is this guy, square root pi 1 minus pi over n, right? Or we can write n is equal to me, right? So since we don't know pi 1 minus pi, but we can do the maximum, we can do the most conservative one, right? We can figure out, consider that is the worst case scenario, which is half, right? Remember why half is the maximum variance, because you are doing a draw on whether yes or no, right? The highest variance, remember when we learn Benoni distribution, the highest variance is you don't know whether they are yes or no, right? Because average is half. So the variance, sometimes is 1, sometimes 0, is the highest variance. So take the worst case scenario is 1/2, right? So this guy, 1/2 times 1/4, 1/4 square root is 1/2, right? So then we're done. So basically take this 1/2. I have this in the slides already. Okay. The picture is already in the back, in the next slide. So don't worry about this. Already in the slide here. Okay, you see, right? The best case is, the worst case is 1/2 and 1/4, right? This is the math, right? Because pi is 0, pi times 1 pi is 0. Pi is 1, this is also 1. And it's increasing and then decreasing. It's like something you will do next Wednesday. You know what's next Wednesday? Next Wednesday, Chongyang Festival. Chongyang Festival is where you would climb mountain, right? Climb the mountain, right? I don't know, but you should do it because it's the best time to do in the season in Hong Kong. Hong Kong is a lot of famous mountain. You should do the hiking in the fall. And anyway, you hike this mountain, you can left and right the same. So the highest point is 1/2, with the height 1/4. So that means the formula is simple. We just replace the calculation by 1/4 here. Okay. And everything will solve easily. All right. So you do the same procedure. If you want to be, the data is within 0.1%, okay, then you almost like 100 observation. Okay. Of course, you can follow the math here, because the same thing, just only difference is pi times 1 minus pi is not come from the question, but you take the worst case scenario, which is 1/2 times 1/2, it's 1/4, right? And you can see if I want the precision to be 0.1, then I need around 100 observation, right? If I want it to be, say, 0.01, right? Then how much I need? How much I need? How much I need? Okay, if you don't know, let's do Excel. Since actually it's easy, if you know math, they're easy to see. Okay. The formula is like this, right? 95%, the Z actually is like 1.96, right? And our pi times 1 minus pi, it's very simple, it's 1/4. Okay. Our margin error, if I 1.1 is like this, right? Okay. Then our sample size n, right, is equal to this square times this number and over the ME square, right? You remember this is the formula we have, right? The formula we have. Still, okay. So if I do this, you need around 10,000. Sorry, 10,000, right? And if you just want 0.02, it's just 2,000. And you want 0.5, it's 500, right? If you want 0.3, that is like 1,000. Why I want to focus on 1,000, the number? If you ever look at the US election poll, okay, they often do the survey within 1,000. And they will tell you the margin error is like 2 to 3%. That's how it comes from. Okay. So that's why if you do 1,000, okay, survey, then you have margin error of 3%. Okay. And then if you want your 2%, then it's 2,000. So that's why they don't really go to 2,000, right? Because the gain is not a lot, right? Unless you really want to be very precise. And if you want further precise 1%, then you have to go a huge number, right? So that explains a lot about election poll, right? And very often when you see things do in Hong Kong, they only do like something like I think they do something like 5? No. Very often they do 500 to 600, 600, 700. So it will be something like margin error like 4%, right? So I recently, if you take subway, then I think yesterday there's a famous survey done to the primary school and secondary school student. How many of them have cell phone, they ask their parents and figure out that 2/3 of the students have the cell phone on their own, and they want to increase the age of the cell phone ownership to 14 years old. But anyway, but the survey they do is only 700 parents and ask how many kids they have their own cell phone. So the reason why I said 600, 700 is done because they only have the 4%. Okay. So that's pretty much what I want to say for this one. And after the break, I want to end this set of slides by telling you two functions, which I do quickly, will be the confidence knob and confidence key, which directly give you the answer of this one, because this will give you the margin error. You give them what is the alpha, what is the sigma, what's n, will give you this formula. Okay. Confidence T will give you this. I don't find this very useful because it saves a very only little calculation. But if you want, you can have fun with that. Okay. And this tells you how to do it. Okay. But I can illustrate a little bit after the break, but there's nothing very new here. Okay. After the break, let's continue a journey on hypothesis testing. But as usual, I know your type. Let's a break of 15 minutes first. We'll resume at 15 minutes later, maybe 2:35. Okay. Okay, rest. Good. I hope you have a nice break. What is different between chapter 4 and chapter 5? The first question I have. Chapter 4 is sampling distribution. So basically talk about what sample mean would look like without guessing anything. Okay, so it's the foundation chapter. And that is extending from chapter 3. Right? Chapter 3 tells us what kind of distribution you might have and tell you the sample mean look like a bell curve. Okay? And chapter 5 is asking when we get something, how to guess. Okay? Involve guessing. And actually, you will look at topic 6, hypothesis testing, we got the same thing, right? So there's 4 is the foundation and 5 and 6 at application. So if you know the information about the 4, then will be similar. Is it 4 and 5, right? Yeah. I will answer your question. So 4 is the foundation and 5 is application. So I hope I answer your question. And the reason why you don't see it different because we didn't go into great detail on what can be estimated, and that will they are very different topics if you go into greater details. That's great. Oh, you can replace pi times 1 minus pi with 1/4. That is because that is you are using the most conservative estimate because it can be any number, but you want to use the highest one to make sure that the sample you collect, in the worst case, will still fall within the range. Okay. Of course, if you know the pi with great confidence, you can use the smaller one, right? You don't have to use this 1/4 because this is a worst case scenario, right? You waste a lot of money if you actually don't need, right? If you have a good idea what they are. That's good. The speed is okay. Most of you can follow. Okay, we have slightly better today. At least not more than half people say you are very tired. Okay, we now have this and goes up. Okay, at least I feel at least now we have 2 here. Someone is not so tired, although some is already sleeping. I guess you're very tired already. I understand. That's okay. And as I told you, when I was sick on Saturday and Sunday, or also I stay at home, I watch someone teaching physics, right? Because someone, I mean, I don't know what to do. I watch some math or some physics, and then I can fall asleep quickly. When I was very tired, I take a medicine, but I can't really sleep. Then I just watch those teaching, then it's very quickly fall asleep. So I record this class with the same intention, right? If you are tired or you're sick, you're nothing to do, play the video clip, and I think you can get sleep very quickly. Okay, that is the plan. No? Okay, good. So now you will see the hypothesis testing. That will be the knowledge we use is not too far away from our estimation. So the idea is very similar. Okay, and it is similar because it is closely related to chapter 4. Okay, and chapter 6 is hypothesis testing is not too far away. So don't worry. Chapter 4 already you understand the foundation is there. Okay, and chapter 5 and chapter 6 very similar. Later you will see. Okay. So hypo testing, we will have two different parts. The first part is one sample. The second part is two sample. Or one sample means we only have one data set. The two sample we have two data set. Okay? And the two data set will be something closer to the A/B testing. Okay? But we focus on one sample first. But because two sample will be very similar. Okay. And one sample is also very useful when we do a lot of hypothesis testing. Okay. So first is what hypothesis testing. Okay. To do so, let me draw a graph to explain what's hypothesis testing. So remember what we're going to study is our population. We want to know a lot of things about population. Maybe it's mean, maybe it's variance, right? And very often we don't know this number. If we want to guess this number, right? What we're going to do is to the sample, right? The sample can calculate X bar. These are all statistics or estimator. And X bar will be a good guess for mu, and S square will be a good estimator for sigma square. We know that already. A good point estimator, if you want. We also learn interval estimator, right? X bar plus minus Z alpha over 2, sigma over root n. What we want. If you know sigma, if you know, then it will be n minus 1 alpha over 2 S over root n, right? So that either way you will be getting what we want, right? Or if you have a binary data, that will be P plus C over 2 square root P1 minus P over n, right? So that would be either way, right? Use the data from sample to guess population. Okay. Now that is called estimation. Now suppose we are going to do the other way around. Okay. Is we know something about this, but we never know, but that we know is what we call hypothesis. We have some assumption, we have some idea, or from past information about this mu and sigma square. Maybe from past estimation, maybe from a knowledge you generated from engineering, or from the boss, from the client tell you this the number. You want to see this hypothesis is supported by the data. That is called hypothesis testing. Okay. Let me repeat. Hypothesis testing is with some idea about the mu and sigma square. We want to see the data is supporting the hypothesis. And probably ask where hypothesis comes from. Can be come from past estimation, come from the claim by, say, by the firm, by outsider, right? For example, we do hypothesis testing for, say, if you're government, you want to see someone say a drink have, say, 5%, say, we look at a beer, right? They say 5% alcohol, right? And then you want to check if it's exactly 5% or not, right? You want to see, right? And that will be hypothesis testing, right? Or they say the coffee has only 1% caffeine. You want to check if it's true or not. Or they have enough preservative, right? There's a lot of harmful substance or good material that you want to check. Or in auditing cases, you want to see if the claim by the client said, okay, in a warehouse, 5% of the goods are maybe defective, right? Maybe helpful, but it's put there due to they're being defective because of their maybe a food industry, they are maybe have to throw away, but we still keep 5% here. They will depreciate, right? You check those. Okay. So these are important, right? Also, the important by itself is later you see when we run regression ANOVA, we estimate the model. We want a model to be useful. We want to check the model parameter is going to be 0 or not. So these are very important tools. Or later you will see A/B test. You want to see, okay, this is the setup of your website, okay, the standard one. I want to change the new looking and want to see the new looking actually will attract more internet traffic, right? You want to compare the two cases. That's called A/B test, right? You compare the difference, and that requires two sample testing. You want to say the two are different, right? Or one better than the others. Okay. You have some hypothesis. You want to see whether data supporting your judgment. Okay. So that would be the idea that behind you want to use data to see if what you think about what's going on is true or not, right? Use the sample to see whether the data support your idea, okay? It's not to guess, but rather reversely, you want to see our initial assumption or support by data or not, okay? Okay, that is the idea. So as I said, it's trying to see whether the claim is supported by data or not, okay? And we will reject if this is not supported by data. So we keep it if it is okay, okay? So we assume it is all right, okay? And reject if not. So that is for those who are in the law school or study law, that's very natural in the courtroom system. Your assumption, especially in the Western system, you assume the defendant is innocent until it's guilty. So the initial hypothesis is say the defendant, no matter how evidence is right now, he is innocent. And to prove he's guilty, you need evidence beyond reasonable doubt. Okay, that is the system in the common law, right? You assume people are innocent. But in China or many places, you assume to be guilty, right? You have to prove that you're innocent, right? So that would be the other way around, right? That's, well, of course, I'm not a legal expert, so I don't know whether I'm right or wrong, but this is what I read from that. But if you're not a lawyer, then probably you know better than I do. But that is so I know at least the British system, you assume to be innocent, okay? Or at least in China in those days, right? You assume to be guilty, right? So we just so that's why we have the null hypothesis and alternative. Null is the one that we have at the beginning, right? It's like what we said is the British system, you assume people innocent. That's a null. Okay? In our cases, you have to claim about the value of the population parameter, something about the value of the mean and variance. You say the mean is 0, mean is 10, mean is 20, variance is 30 something, okay? You have some idea. Where it comes about, either from prior knowledge a prior estimation or some working assumption that come from somewhere else. Each denoted as H null or H naught or H zero, which is something we start. And the other is called the alternative hypothesis. Is we try to see the evidence is supporting this or not. Okay, if evidence go in favor of the alternative, then you will try to reject the null. Okay, and this is called H1 or some book called HA. Okay, it depends on the book you read, but these two must be mutually exclusive. Okay, but need not be exhaustive. But that is the idea. Okay, so you have to know the first two terms: null hypothesis and alternative. Null is the thing you start with, and alternative is where you look at data, right? The data supporting or not. Okay. And what is hypothesizing? Hypothesizing is basically you would, at the beginning, you specify the region or specify what are the value that you would reject the null or you don't reject, right? Or sometimes you could accept the null. Okay. So the rejection region is the things you could reject, otherwise called accept, right? In that case, for example, in the murder case, right? You would be saying that right. What's certain regions? If the guy is not in the same country on the day that murder happened, right? Usually you're not in the scene, then you are not there. Then it's very likely that it's going to be accepted as you are innocent, right? You can't kill people, right? Unless you're a superpower, right? Suppose the guy died yesterday in somewhere in Hong Kong, right? And you can prove that you are actually in North Pole or in the moon or in the Mars or in somewhere, right? So really, unless you're a superpower, I can't kill it, right? Then we accept you're innocent, right? And what is rejection region? Maybe something like, okay, you are in the scene, you hold the weapon that you kill the guy, right? Or there's a video that's showing you actually kill the guy, then you can't run away, right? So that is rejection region. It's like you have to define what kind of evidence, right? That is beyond reasonable doubt. Okay, we have some idea there. Okay, so now we have some other terminology. I'm sorry, but because it's a new topic, so that's why, unfortunately, I have a lot of terminology. So we have what we call the simple and composite hypothesis. Simple hypothesis is very simple, which means that we are saying a population parameter is equal to a particular value. So it's mu is equal to 3, that's it, or mu equal to 4, sigma equal to 3, that's simple. Composite is more than 1, so it's not, everything is not simple, it's composite, right? So when you say a population parameter mu less than 3, more than 3, not equal to 3, they're saying that mu is more than one value, right? Less than 3 can be 2.99, 2.8, 2.7, right? So if you're going to claim a range, then it will be composite. Okay. So for our discussion to be manageable, we'll focus on the following restriction. Our null is always simple. Our alternative is always composite. Okay. You may ask, how are we going to do if things are reversed? Yes, it can be done, but it's way beyond our class. Okay. I don't think anyone in undergrad would study this beyond this scope. Okay. So it's okay to keep that unless you go to STEM department. This is something that it's okay to keep. I think even in B school, in the grad level, we still keep that as well. So no one actually go beyond that. So that's okay. So don't bother yourself to ask why. We focus on this because beyond this, the math is too complicated. Okay. Of course. Now the good thing is with AI, you can ask what happened. Okay. But I don't think you want to open the Pandora box and then you always things comes out, right? So I think now the thing is like the knowledge is easy to get. So the problem is not you don't have enough knowledge. It's to limit yourself what is understandable, what is not. So I think we spend enough energy to make ourselves focus on something we can do. So I hope that is okay. So that means that our now is always equal to some number, simple, okay? And composite with two types. Later we will see why with two types and it's important. And the method is a little bit different, okay? So alternative can come in two types. One is called one-sided, which means that we hypothesize the alternative is less than or more than. The other case is two-sided, not equal to. So the question probably come into mind would be, when should I use which, right? Because the now is always simple, it's equal to something, okay? The alternative is there are three choices here, okay? What should be your choice, okay? The thing is, I tell you how you can use which one of the three. If you have no idea what to do, no information at all, the default choice is this guy, okay? The default is not equal. You're testing equal versus not equal. That's default. But the question is, when you use one-sided and when you use less than or more than, okay? It depends on application. What do you mean by that? You ask yourself when you will take action, okay? Suppose you are government, you're checking a particular food, okay? You want to make sure that the harmful substance like preservatives or coloring cannot be more than a certain amount, right? In that case, you will take an action if something is too large, okay? This is the thing you take, right? You want to see if this is sufficient large, you take action. So that is more than. If you want to take action, if it is too little, you want to take action, right? Suppose some medicine, you say the active ingredient should be this much, right? If too little, then you're not going to use the medicine. Or someone claim the milk, right, has to a certain percentage of milk, right? Otherwise, you put too much water there, right? It's cheating, right? Then it must be this guy, right? So that is depend on what your particular choice. But if you don't know, always two sides. Only if you know there's some severe consequence to take action, then you will be choosing the other two. Okay. So let's see the example, right? So I showed here, right? If quality control or harmful substance will be more because more take action. So main ingredients will be more, doesn't harm anything. Less to take action, so it is less than. Okay. But so let's see example. Okay. You are doing a consultant for a local club. Okay. And the question is now because of aging society, people get older. So the customer age is whether it's more than 45 or not. I'm going to check this one. Okay. And if you're not more than 45, then you basically use to keep the old, continue the system. Otherwise, you want to make it cater to older, right? So that's why, remember our now is always simple. So that's no need to do anything. You will take action if more than 45. So this is our alternative. Is that clear? So The alternative is things that you want to take action, right? So that is, you put more there. Is that okay? Because if not more than 45, actually you don't want to do anything, right? So we just put there. When two side you don't know, then you would do two side, right? So for example, if you're auditor, if you want to see the firm claim the reference is $3,000, as auditor, you have to validate it's true. And when this is more than 3,000 or less than 3,000, you are not happy, right? So the alternative is not equal, because more than or less than, you would say something, right? So that's why that's the case. Is that okay? Remember, our null is always equal. Our null is always equal. Is that okay? Now, once of that, we will define hypothesis testing, and it will involve what we call test statistics. Okay, although I put it gray here, it's technical, but you will see. Okay, usually hypothesis testing will specify a called test statistics. Remember, statistics a function from a random sample. Okay, test statistics a number calculated from the sample. Of course, it's a function, but it's at the end, once you calculate the number, right? And this number will tell us, based on the region, okay, acceptance region, okay? And if this number fall within the acceptance region, you accept. If the region is reject, you reject, okay? And the boundary between accept reject is called critical value, okay? Don't worry, we'll define this later, but I put it here because usually we want to define this one, okay? But I just, since I'm not asking, so that's why I put the gray area here, okay? Let's see the example. So I have the sample mean, okay? If I have null hypothesis is like H mu is equal to some number A, right? If the alternative is mu is bigger than A, right? So for example, I'm talking about a food company claim their ingredient, so the food has harmful substance less than A, right? You want to see it's more than A. You want to test the guy is honest or not, right? And how can you test it? You would say, okay, if I look at the sample of your food product, if the average is large enough, then you will reject it, right? You're in favor of this alternative, right? So, but how large is large? Of course, you have a critical value, right? If sufficient large, then you reject, right? You go for the H1, right? And similarly, if the H1 is less than, it means that if you found a substance, the mean is super small, then you favor this H1, right? If this is not equal, that means that extreme, you reject. So let me draw it because I think it's a little bit too tricky here, okay? So suppose you claim your mu is A here, right? If your data is exactly mu, which is A, then you would just say X now is true, right? And it's somewhere nearby. So suppose our case is mu is A, right? And our H1 is mu is bigger than A, right? So in that case, if our data is here or even here, then we will not reject our null, right? Because there's no evidence to say this guy, right? And only if this is big enough, how big it is, maybe somewhere here, okay? This is called the critical value. Okay, and we will say this beyond is too large, is called the rejection region. Right? And this is acceptance region. Okay. The question is how big, how far, or how to set the critical value. But as we agree, if this is super large, then we will say large. Okay? And how large it is? Actually, I don't want to go to the math at the moment, but you can imagine how do we say how large it is. Why? Because if we follow the bell curve, okay, that means that 95% will be within 2SD or 1.96, right? So basically, how far it is just 2 standard error, right? If you know the sigma, that is sigma over root n, right? So if it is within the distance of 2SE, then you would not reject. If it's beyond 2SE, which is not possible from our perspective, then we will in favor of H1. Okay, we'll talk about this 2SE later or next class, but that will be the main goal, right? So that's why you will see our chapter is not too much different from estimation. Although we don't do estimate, but the idea is very similar to that idea. Is that clear? Right? Because it's very similar to doing the interval estimator idea. Okay, extending this for 2SE. Is that okay? Is that okay? So this is the main idea that behind what we call the rejection region. Of course, if these are left-hand side, the rejection region on the left-hand side. Okay, but let me go to the detail. So I don't think I will have time to go over that, but I would just go over the terminology here so that next class will go faster. Sorry. So here we have to define some terminology. Because when we make decision based on data, we have to make some error. Because then there's no 100% sure, because we don't observe everything before we make decision. So it's always error. And the type 1 error is it is correct but reject it. Okay. The null is right, but we reject it. Okay. And that is known as false negative if you go to the medical school. And the probability of making type 1 error is denoted as alpha. Okay. And alpha, the rule of thumb will be 1%, 5%, 0.1%. Okay. You will see I use alpha, then later you will see that it's not coincidence when we talk about the interval estimator. Okay, that is not a coincidence. Why I use 1 minus alpha there? Okay, it's very closely related to the idea when we do interval estimate. Okay, but let's take this notation first. You will see why. Okay. And technically, this means that null is true. We reject it, it's called alpha. Since the type 1 error, you can imagine that that's actually a type 2 error. Okay. The type 2 error means that actually the null is false, but you fail to reject. That is called a type 2 error. So to give you an idea, what is type 1 error? Type 1 error is type 1 error. Remember, in the cost system, this guy is innocent. Okay, but you send them to jail. That's type 1 error. So you incorrectly imprison the innocent guy. That is type 1 error. Okay, that's alpha. And type 2 error is type X0 is false, means that that guy is a criminal. You let the criminal go free. It's type 2 error. Okay. And in the court system, at least the British, you would worry about jailing the wrong person rather than let the criminal free. So that's why type 1 error is more important than type 2 error. Okay. So that's why in our class, we'll focus on type 1 error. Okay. And one reason also is we focus on type error is we can't really control type 2 error. We can directly control type 1 error. Okay. Type 2 error is determined by the way you do the testing. Okay. You decide how you do the things. So it's something you can't really control directly. Okay. Once we set up how we do it, you can't really do too much. So it's just you can control only alpha. Okay. And that's the reason why we often at time talk about type 1 error. Okay. And there's always the trade-off between the two error. If you are going to reduce your type 1 error, you will increase type 2 error. Okay, so there's no free lunch. So that's why very often we said type 1 error is 5% or 10% or 1%. That is a thing we think that is acceptable level. Okay, and you will ask, can we reduce type 2 error or type 1 error at the same time? Yes. If you collect larger sample, both of them can be reduced. Okay, but if the same sample, we can't do too much. Okay, I think I should stop here. Otherwise, I would go for time. So next week, we'll continue our journey on this. Okay, but you will see, as I said, already give you the idea. It will be not too much different from hypothesis test, interval estimate. Okay, it's at least for our one sample test. Okay, so I will see you next week, Monday, and the assignment will be released also over the weekend or next week. Okay, enjoy the weekend. I will see you on Monday. I say I want to answer the question you might have.